Hi there, welcome back. What we're looking at today is a report on a repair of this Melos SHA headphone amplifier. In trying to find information on this, I found that there is no real detailed description of this circuit on the web. There's certainly no schematic available for this model, and that makes repair very difficult, and that's what I found with this one. I ended up having to dismantle and desolder just about every component on the board to find the problem, which I'll describe shortly. And because I had done all that desoldering, I was able then to draw out the circuit, basically reverse engineer it. And I'm going to be describing that circuit later on in this video. I think it's the first time that the actual schematic of this model is presented here. The SHA has three inputs, 1, 2, 3, and a line output at the back. There's a selector switch for the input on the front here, and a volume control. And the one used here is an Alps Black Beauty, which is a very, very high quality potentiometer. The power switch here switches on the power and results in a red LED coming on. That red LED stays red for as long as the tubes take to warm up, and subsequently the output relay switches on, connecting the line output to the system, and the LED turns to green. It has two headphone outputs over here, plus, as I mentioned, the line output at the back. Now, having described the amplifier, let me tell you a bit of the things you don't see. This design is incredibly unusual. Nothing makes sense when you first look at it. The fact that you can't find a schematic anywhere just makes it worse. And when you do find forums that discuss the Melos SHA, invariably it turns to description of the Melos Gold, which is the next stage up from this one. And therefore, if you do have an SHA, you're just left extrapolating, trying to find out what this thing works, why this thing works, how this thing works, and how to repair it. Although this sound is supposed to be heavenly, I can only describe this build as the headphone amp from hell. And I mean that, I was going to say in a positive way, I don't know how you put it, but the result is amazing. How you get there is absolutely crazy, all right? I suppose if you are an inspired audiophile, you are a little bit crazy in a good way, and this thing just stays in line with that theory. Because although the circuit itself produces incredibly good results, the actual build is the weirdest build I've ever seen. The PC board is double-sided, and all the traces on here look like they were done with a Sharpie. Certainly no software was used to lay this out, because nothing matches in terms of left to right channel. It's completely sporadic how the components are laid out on the board. And just to add insult to injury, the one channel is actually built different to the other one, and I will show you that when we discuss the circuit. This particular one here, if you know this amp, you'll see that a lot of components have been swapped out. And the reason for this is that this particular amplifier has been messed around with by more techs than I'd care to mention. The result was a mishmash of component changes, of bad soldering, I just can't tell you how badly this thing was played with. Every guy that came here trying to find the fault, which I'll talk about in a minute, just played around, just guessed at what he was doing, hoping that the result would be a fix. But unfortunately, the result was them giving up and leaving some of the hacks they did along the way unrepaired. So I found bad soldering, I found wrong components, I found components soldered in the wrong way, and that's just to mention a few. The board was absolutely filthy. When I started trying to trace the problem, I ended up having to clean the board so I could see what I was working on. And later on found that some of the soldering was so bad I had to desolder just about everything. And in doing that, I decided to do the drawing of the schematic. And I think that I'll be able to describe later the only schematic on this particular, for this particular amplifier that is available, talked about on the web. So the main problem with this preamp, or amplifier, which belongs to a friend of mine, was that there was a crackling on the one channel. And this had been the problem from day one, which started probably, he says, over 20 years ago. Since then, it's been in the hands of numerous techs, and the result's still the same. So when he gave it to me, I wasn't too hopeful of finding a solution. My logic was, I'll go on the net, find a schematic, work through it step by step, and find what the problem was. That's where I ran into the first difficulty, and that is that there is no schematic on the net. The one that's available is for the Gold version, which has certain similarities, and it did help me to at least identify some of the components, but it's certainly not on this particular amplifier. When I thought about the problem, which was happening only on one channel, I followed the signal through, and I came to the conclusion that it had to be something to do with this DC offset servo over here. Now that preamp over there, or that op amp over there, is used to null any DC offset at the output to your headphones. So I looked around here, and the problem was actually quite simple. This thing has got two pots over here. The ones that were in place were single turn pots, and that's what you use to null the DC offset at the outputs. Ideally you need 0 volts. And one of them was faulty, this one over here. So I replaced both of them with 10-turn multi-turn pots, and so the first problem went away. The crackling went away. And I thought, hey, it's done. Until I started measuring some voltages around here. So when I measured the supply voltage of this op amp, I found that the positive supply was plus 6.4 or 6.5, and the negative supply was minus 8 point something, which was a bit weird, because this should be a plus minus 6.3 volt supply. I then had to trace back, and I found that the negative voltage regulator had the one pin disconnected. It was soldered, but because the soldering had been badly done, one of the traces was not making contact. When I put that in place, I ended up with the plus minus 6.3, 6.4 volts as it should have been. So that was resolved, right? So that was problem number 2. Problem number 1 was a crackling, that was gone. Problem number 2 was that supply. The reason that supply was so important is because the minus 6.3 or 6.4 volts that you get out of here is actually what drives the heaters of the tubes. So the tubes were getting minus 8 volts instead of minus 6.3 volts. So that was probably going to kill the tubes soon enough. The other problem my friend told me about is that when he plugged in a headphone into this jack, the output, the line output, was muted, which is what it should do. When he plugged one into this jack, the line output did not mute. I looked at this carefully, and I found somebody had desoldered this thing and then resoldered it wrong. So I fixed that. That was easy enough. So that was problem number 3. Another problem was excessive heat coming from this voltage regulator IC. This is a high voltage variable voltage regulator, and it is programmed with the resistor setup to provide about 110 volts. And the result was the voltage coming out was not steady, it was wrong, and this thing was heating up like crazy. I then looked further and found this thing had been soldered in the wrong way around. So that was problem number 4 solved. And fortunately, the IC had not burnt out yet, so that was repaired. Another annoying problem this thing had was it took a hell of a long time to switch on the output relay, which would switch the headphone out through these 2 capacitors to the line out. It was taking over 3 minutes. Now the logic with this, there's a timer circuit here around this relay. This is a MOSFET, there's a capacitor, there's a diode and a resistor in there. And what this would do is it charges the capacitor, and when it reaches a certain level, switches on the MOSFET, and the relay is activated, passing the signal through to the line out. This was taking about 3 minutes, which is a hell of a long time. And the reason you need some time is that if you switch this on and the tubes are cold, there's no sound initially. So their idea was let the tubes warm up and then pass it through. This timer does not activate the output of the headphones. If you switch it on and it's cold, it'll take a while, 20 seconds or so, before you hear sound coming out. But there is no timer relay. So this was easy enough to resolve. It was just a question of reducing the size of the capacitor from 4,700 microfarads to about 1,000 microfarads. And we now got this thing coming in at about a minute, which is fine. And as if that all was not enough, when everything was done, the sound was fantastic, but there was still some noise on one channel. And that noise was actually manifested by looking at a speaker cone when this thing was connected to an amplifier. And what was happening was that speaker cone was moving at a very low frequency. So there was low frequency noise which you couldn't hear, but it was there. And what that turned out to be was a faulty JFET in the constant current source used to bias the tube. Now, this was a bitch to find because it wasn't faulty. It wasn't always faulty. It was intermittent. So the only advantage I had here is one channel was fine and the other one was showing those symptoms. So what I had to do was start swapping things around again. And when I swapped this JFET to the other channel, the problem followed it, which led me to conclude the JFET was acting up. And I then looked for equivalent JFETs. The way to do that was, because I didn't really know what JFETs these were, was to measure the actual constant current that this thing was sinking, which was about 4 milliamps. I ended up using the, the 369. We'll see that in the schematic. And I got this thing to sink constant for 4 milliamps again. Put that in there, the problem went away, replaced the other side just to get it equal. And it seems that we have a fully working headphone amplifier again. And so the next stage of this video is I want to show you the schematic, describe its function, and hopefully help anybody that meets one of these beasts in the future. Certainly it'll help prevent some of the mess that was done on this one with haphazard repair attempts. Absolutely no logic with some of the things that were repaired here, simply because people had no information. Right, moving on. As promised, I'm going to go through the schematic step by step and show you how this thing is designed. Now, I'm going to start off by saying I'm not going to have this schematic available to send to anyone. I'm going to make this video as clear as possible. And so if you want the schematic, it'll be available here. You'll be able to see every part of it. But I really don't have time to be sending schematics out, so I hope you forgive me for that. But you'll see it's all described here. So if you have a circuit and you want to see how it works, just go through the video. Right, start off. Let's go to the high voltage supply. The high voltage supply starts with the input of 120 volts or so from the toroidal transformer. It goes through a bridge rectifier here, and there's a filter cap of 560 microfarads, 400 volts filter cap on the output of that to smooth out the rectified DC. There's a 180 ohm resistor in line, and then it goes to the input pin of the high voltage adjustable voltage regulator, an LM783. And here you have a normal configuration for setting the voltages. You have a 511 ohm resistor between the output and the adjust pin, and then you have a 43k resistor to ground. If you do the math with one of these, for one of these regulators, the output voltage comes out to about 108 volts. And we get near that. Then there's the two flyback, or rather the two diodes that are used in here just to discharge and avoid damage to this IC if you switch it off and you still have voltage on these capacitors. So those two diodes there, one N4007s, is just there for protection. What they've done here is they've also stabilized the reference voltage over at this pin, at the adjust pin, with a 100 microfarad capacitor and another 100 nanofarad capacitor in series. That just keeps this very stable and reduces the ripple on the output. Again, this is very standard for the design application notes for this kind of IC. The output here of 108.5 is the calculated value, is then stabilized further, smoothed further with a 1000 microfarad capacitor and another 100 nanofarad capacitor to get rid of any noise on there. There is also a 20k resistor here, which is simply to bleed away the voltage when you switch this off. So this is a bleed resistor to avoid this line from staying at high voltage when you switch it off. And that basically is the high voltage supply. Here's a close-up so we have no doubts as to the details of the circuit. And here we have the low voltage supplies. It's a plus, a positive and minus, a negative supply. And that is fed by these center tapped trio of pins of connections coming from the toroidal transformer through a bridge rectifier. That middle pin goes to ground, okay? So this thing is smoothed with a 4700 microfarad capacitor to ground, that line over there. And 4700 microfarads there, 4700 microfarads for the negative portion. Then you have two 2.2 ohm resistors before coming into the regulator, voltage regulator, adjustable voltage regulator IC, that one there and that one there. Then we have a positive adjustable voltage regulator, the LM317 at the top, again with a 511 ohm resistor there and a 2.1k resistor there. If you do the math, it comes out at something 0.6.5 volts, which is close enough to what we get. That is a protection diode as well for the charge on this capacitor and this capacitor when you switch it off. Now what you get here is they've put in a 2200 microfarad and a 1 microfarad in parallel, again to smooth the reference voltage, which again serves to reduce the ripple on the output. The output there has a 10,000 microfarad smoothing capacitor, which is pretty much overkill, but it's there. And in parallel with that, a 1 microfarad capacitor. So that is the positive side. The negative side is pretty much the same, but in reverse. Nothing strange or unusual about the circuit at all. If you look at the application notes of both the 317 and the 337, which is the negative version, this is exactly what you'll see there. So here's a circuit again for anybody who wants the detail. Pretty straightforward. So the result of this is 6.5 volts positive, and we get pretty close to that. And minus 6.5 volts, and we get pretty close to that. Now, the circuit for the gold states this should be 6.3 and minus 6.3. But this is what we are getting on this one. And that pretty much completes the power supply description. The actual components used are very high quality. Some of these values are way overkill, but again, whoever designed this got it right. Who am I to criticize? But if you've got one of these, you can see the components on the boards themselves, so this will just tell you how these things are wired up. And here's the schematic for all the audio section and protection section, which is where all the magic happens. Now, I've got this drawn in a way that I believe is pretty logical. This is the one channel on the left here. This is the other channel on the right here. This here is the heater circuit for the tubes. And this here is the relay protection and the output, or rather the power indicator LED, which goes from red to green. So I'm going to go through all these sections separately, and hopefully you'll then get a full overview of how this thing works. Let's start with the audio when it comes in. What we find here is pretty standard, but we'll go through it step by step. Your right input, this is the right channel. Your right input comes in here, and it comes from the input selector switch, which I haven't drawn here because that's pretty straightforward. It comes through a 1 microfarad capacitor, which should be a polypropylene high quality capacitor because this is the first cap in the audio path. And it then meets a 1K resistor going to the grid of this first triode in the first tube. And that has a grid stopping resistor of 1K. So basically your signal then comes in here, and we then have the biasing of this triode done in a rather unusual way for this kind of circuit, but it is basically done with a one diode over here, which gives it a 0.7 volt drop. But you need a constant current source. You would normally either have a resistor over here to ground, or in this case, a constant current source. And the reason for that is you want a very high impedance in this point of the circuit so that your feedback works, and I'll describe that in a second. So your constant current source is basically a FET, a JFET. In this case, the one I used is the 2SK369. And it is set up in such a way that it produces about 4 milliamps of constant current sinking capability. So basically, you've got 4 milliamps being pulled down here. These are 32 volt diodes in series. And the reason for that is to minimize or to limit the voltage that you will see at this point when this thing goes into operation. If for some reason this thing exceeds 2 times 32, 64 volts, the current will start going through there. So basically this is just over voltage protection. These are, and I'll repeat, 32 volt diodes throughout. Wherever you see the diodes, 32 volt diodes. So you get your 4 milliamps coming down this point here, and the only place they can really come from is from the cathodes of the two triodes. So this would be a matched pair of triodes inside one glass tube. So you'd expect 2 milliamps there, 2 milliamps there, 0.7 volt drop over here, which means that the difference in voltage between the cathode and the grid would be about 0.7 volts. Because if you call that 0, that'll be minus 0.7, and that will be, there's no current in there, it's a high impedance path, so that will be minus 0.7. And you've biased your triode. On the opposite end, on this side, you have a similar situation, but in this case you've got a capacitor coming through from the output, and we'll see that in a sec, into this grid. And what I believe this does, it's basically a negative feedback situation to reduce distortion. So you've got negative feedback coming in. This thing's acting almost like a differential or summing amp, because this is negative feedback. And again, the similar situation here, 1K and 1 meg to ground. There's a 1 microfarad capacitor here which basically bypasses anything below a certain frequency or above a certain frequency. Don't ask me the exact details of how this works, but that's what's there and that's what's working. Let's go up a little bit. So what we see here is that the signal comes in here, gets amplified. In this case it'll be the differential signal, and it then goes through a load resistor, a anode resistor, plate resistor, you could call it as well, to the B+, to the positive supply, which as we've seen is about 110 volts. This plate resistor is the same value, but it has a bypass capacitor of 27 ohms, which tends to 27 nanofarads, which tends to smooth some of the high frequencies a little bit. And this is a strange configuration because it's actually smoothing the feedback, but my friend who loves this preamp swears by the difference that this capacitor makes, and this is exactly where he wants it to be. That's exactly where it's been left. The audio signal then comes out of here, up there, through that 1K resistor, and then it has two 1.5 microfarad coupling capacitors, film caps, over here, and that's the next part of the circuit we'll describe. So here we are, we've got our signal over here, and it meets another JFET, a 2SK117. This is a very high impedance path. It's a buffer. Basically, this is a buffer between the current driver transistors for the headphones, for the output, and the tube circuit over here. It creates a very high impedance path. And what you get there, if you ignore this diac, 32 volt diac again, ignore it for a sec, signal comes in here, and it's basically set up as a source follower. So the signal then passes through to here, through this 2.2K resistor, into the base of the output Darlington transistor, a 2N60545, and your signal then comes out here. That's your right output to your headphones, straight to the headphones, okay? The few things that are in here that need describing, this diac here is set up to, again, reduce voltage, excessive voltage across the transistor. I believe this will only come into operation if something goes seriously wrong with this JFET. So this is a voltage limiter. I really don't see why this is needed, but it's there. Same thing applies to this one here, 32 volt diacs. They're all 32 volt diacs, okay? If we look at the output now, we've got a line going back, which is that feedback path to the differential configuration of the input tube. That we've looked at already. The other one goes up here and across there through a 100K resistor, and it goes into the inverting input of the first op-amp. Now, what happens, this is DC coupled, so what happens here is that it's measuring the DC voltage over there, and it's going to try to match the output to the same level that you've set on pin 3, and pin 3 has a resistor to ground, and it's basically got a voltage divider over here with that trim pot. One side of it's connected to the positive 6.3, the other one's connected to the negative 6.3, and you adjust it in between till you get 0 volts DC on the output. If there's a few millivolts, it's not a problem, but you want it as low as possible. And this is basically just the servo function feedback, where it's going to try to adjust it to match that voltage that you've set there, and the voltage you set there is by looking at the output and adjusting the trim pot. This is the output then, which drives the positive bias. It sets a positive bias voltage through that 100K resistor to the grid of this JFET. Okay, so whatever happens on the output, you adjust it matching with that thing there, and the op-amp takes care of making sure that the positive voltage bias on the JFET is it the correct value to ensure that this Darlington produces your sound with 0 DC offset on the output. Okay, this Darlington's collectors, the collectors are connected to the plus 6.3, as is the drain there, and the op amp is also driven by the same positive 6.3 and negative 6.3. So there is a 12.6 volt swing minus the limits that the op amp would force, but it's quite a good swing it's capable of providing for the output over there. All right. That basically then is your servo circuit, DC offset servo, your buffer, your current driver, and the previous stage would have been the main audio drive circuit. Okay. The right-hand side should be the same. However, it's not. This is why I say there seems to be a mistake here, but that's what I picked up from the board by reverse engineering it. And believe me, I checked this endless times. What I've drawn here is correct. I think they made a mistake. So what you have here is you've got your signal coming in. We just looked at that. It goes to a 1 meg resistor to ground, or it's ground basically. And then it has a 1K grid stopper, a grid resistor over there. On this side, you've got the 1 microfarad. It then goes into a 1K resistor and then to the grid, but the 1 meg is connected straight to the grid from the grid to there. The other side is the same as on the other channel, but this input is just slightly different. Quite honestly, I don't believe it makes any difference, but it is different. That's why I said somebody had had a few too many vodkas when they drew this, and it's just got built this way. So basically your right-hand channel, your left channel rather, is exactly the same as your right channel that we just looked at. Everything else is the same. Your output there is stabilized with the other op amp in the TL072 or 5532. There's quite a few op amps you can use here. And this spot is the one that you adjust the DC offset for the left channel. So that describes the two main parts of the circuit. There's a part here that I really do not understand, and that is the heater circuit. Now, this tube has a 6.3 volt heater voltage. Pin 4 and 5 are the heater pins. And as I said earlier in the videos, the minus 6.3 volt supply is the one that supplies the heater voltage to this to the tubes. Now, they require about 300 milliamps, so it's quite a beefy current. If you add the two up, you've got 600 milliamps. So it's quite a high amount of current, but that part is fine. The other part is the one I don't understand. By my logic, this output, these pins, these heaters, should be connected to ground, so you could get 6.3 volts across it. Instead, and again I've checked this endless times, one is connected to the output, the right output, and the other one is connected to the left output, which to me makes no sense at all. And maybe someone can explain this on the comments, because what I see here is you're pumping 300 milliamps through an output, which doesn't make sense to me. But that's the way it is. Hey, I really don't understand this part of the circuit. It almost seems there's something wrong here. Maybe there is. Maybe it's just like this, and it works like this. I really do not know. The final part of the circuit is around that the timing circuit with the MOSFET and the relay. And again, this works fairly simply. 6.3 volts feeds up here. If you ignore everything else, what happens here is that this resistor starts passing current when you provide 6.3 volts. It starts charging this capacitor, which here is at 4700. I've changed it out for a 1000 microfarad capacitor. When this thing starts rising, this voltage starts rising, reference to ground, of course, it gets to a point where this voltage reaches the switch on voltage of the MOSFET. At that point, the MOSFET turns on and it activates that relay. Okay, that's all that does there. It's activating that relay. This diode here is to protect the circuit, this from excessive build-up voltage, reverse EMF of from the relay coil. Very straightforward, very simple. The same applies to here. When you switch it off, you want this capacitor to discharge as quickly as possible, and that's what happens there. So again, very simple timer circuit to drive the coil of that relay. Now what happens at the other end of the relay? On the switching part of the relay, there's a part for the left channel and a part for the right channel. If we look at the left channel, it only deals with the audio, and what it does is your audio, your right output's coming here through that 1.5 microfarad. Actually, I believe this is a 6 microfarad. There's an error here. That big aluminium tube, it AC couples the headphone out to the line out, so that's connected over there. And what happens here is when the relay is off, this point, the line out, is basically shorted to ground through the relay connector. When the relay activates, that switches across, and the audio is then, the line out is then connected to the output through there. There is no connection to ground, there's just a 480K, basically a load resistor over here to reference it to ground. And that's very simple. All you're doing is you're leaving it short to ground till the relay kicks in, and then you're removing that short to ground so your signal can pass unimpeded through there. On this side, you've got exactly the same thing. When the relay activates, this short to ground is removed and the signal goes out through there. The only difference here is that when the relay activates, something happens to this circuit over here. They're using this relay for two purposes in this case. And what happens over here is that when the relay activates, this point is connected to ground. Now what does that mean? Let's go up a bit. That line there is at 6.3 volts. That thing is a dual LED, red and green LED, with a center pin with the cathodes connected to ground. So when this thing's at 6.3 volts and that is floating because the relay is not activated, it's just floating, the highest current path would be through here. In other words, this path is active and the red LED is switched on. When the relay activates, that part becomes shorted to ground, so that becomes ground. That is ground, so the current path is now through the top here. That is now off because that's basically 0 volts, and that there is 0 volts. But the path is now through the top here. That LED is switched on, so that's your green LED. That's how your relay changes the color of the power indicator LED from red to green when it activates. So basically we have our entire schematic. And as I said, there's no need, I believe, to send this out. I think it's fairly clear. I can and will do this again. So if we go down here in steps, you can pause this and you can see the whole schematic. There's your heater circuit. Okay, and the relay circuit and timer. And remember, as I mentioned, I believe there's an error here. I believe that's 6 microfarads instead of 1.5. And that, my friends, is the complete Melos SHA1 schematic. It seems so simple, but this bastard gave me so much work and so many headaches. It's hard to describe. I just hope it proves useful to anybody else who's having the same problems that I had. And enjoy, and see you again soon.